Alright guys, so in these first three problems, what they really are just review problems of what we covered the last day. The very first problem is just an evaluation problem. The second one is a composition written the easy way. And the third one is a composition written the kind of confusing composition notation way. So my hope is that when you see all three of these, you can understand that you're really doing the same thing, except the notation is telling you to do a little bit extra for each and every single one of them. So let's try to start with the beginning. Notice that I'm asking you to find h of -1. So I'm asking you to input -1 into the h function to see what your output is. And whatever that's equal to is your output. So in order to do that, let's look for our h function. Notice I color coordinated it for you just to make it hopefully a little bit easier. I don't know how much easier it makes, but hopefully it did at least a difference. So what I'm doing literally is just plugging -1 into my h function to see what it equals. The way I like to do is I like to rewrite everything, my whole h function, but with parentheses everywhere there's x's, so that way I can go back and input whatever my input is. And h of -1 is what you're looking for. This is what it's equal to. Remember your rules of PEMDAS. Is there any work to be done inside the parentheses? No, but there is exponent. So -1 squared is just a +1. Keep in mind that this negative has nothing to do with that square, so it's going to continue being on the outside. Don't forget your +1 at the end. -1 plus 1 is a +0, so you can notice that h of -1 equals 0. So when your input is -1, your output is 0. When your x is -1, its associated y is 0. Okay? Make sense? Cool. Now notice that we have a composition here because notice that in the very inside is our input. We're going to plug it into our f function. And once we plug it into our f function, we figure out what f of 0 is. We're going to plug that output into the g function. So really, it's a two-step that you need to train your mind to see when you see that notation. So let's go ahead and plug 0 into my f function. Well, here's my f function. F of 0 is going to be equal to 2 times 0 minus 1. Doing the math, 2 times 0 is just 0. Don't forget to minus the 1. So you end up with 0 minus 1, which is a -1. So you'll notice here that f of 0 is equal to a -1. Now, we're not done yet because we still have to figure out what f of 0 is. We just did. And then we're going to plug it into the g function. And I'll even change colors green so that way it's a little more color coordinated. Now, this is my g function. I know that I'm plugging in f of 0. F of 0 is a -1. So let me plug in a -1 everywhere there's an x. G of -1 is going to be equal to 3 times a -1. 3 times -1 is a -3. So you can see that this one was a little more straightforward. But again, the value is in understanding the game plan. Once you figure out the game plan from the notation, the rest of it is just take your time. Just start plugging stuff in and take your time. So last but not least is the very last one. Let me move this to make sure that I'm not running into it. So first thing I notice that my input here is -x. And notice that this is h composition of g. So I like to write it the least complicated way just because it makes a lot more sense to me. Now notice that it's a -x, but I'm not going to let that scare me. I'm still going to input a -x into whatever my g function is first, figure what that is, then plug it into my h. So let's do it to the g first. Here's my g function. G of whatever x is going to be equal to 3 times whatever x is. So there are my parentheses. What is my input in this specific situation? A -x. So just because it's -x, don't let it fool you. Just keep doing the math. G of -x can be equal to 3 times a -x, which is just a -3x. Now that you know what G of -x is, you're going to plug it into the h function. Here's my h function. It is going to be h of whatever x is going to be equal to a negative whatever x is squared plus 1. What did we find out to our G of -x to be equal to? -3x. Take your time, do the math. There's no way to combine -3x, -3 times x, so you're going to go ahead and do the exponents. -3 squared is just a positive 9x squared. Don't forget that this negative has nothing to do with it. Don't forget your plus of the 1 that was just hanging out watching the show. Now, is there any way to combine these in any way, shape, or form? No. So that means that you are done. And that is all you have to do. Okay? 100% review, but you get the moral, right? All this inputting and output, compositions, operations, all that good stuff. Good? Okay. All right, so let's start talking a little bit about what are relations and what are functions, because that is what we are going to start covering today. Now this is review because I believe it's an Algebra 1 standard and it's even a geometry standard. So what is a relation? A relation is a set of ordered pairs. Now remember that ordered pairs are just literally, they're the way we write relations. The parentheses with the comma in the middle. Does everybody remember what gets listed first? Is it your x or your y? Your x. That means that your y gets listed second. Keep in mind that when we're talking about x's, we're talking about inputs. When we're talking about the y's, we're talking about outputs. And you can think of this as a function. The x is whatever you input to the function. Your answer is the output. It's what you get out. Now, when I'm giving you an ordered pair, you might not know what the function is, but you know that there's a relationship between these two numbers. This is an input. Let's call it an x. This is a y. This is an x. This is a y. This is an x. This is a y. Each x and y are in a relationship with each other. It means that when you plug in a -1, when you input it, you're going to get an output of 2. When you input a -2, you're going to get an output of 5. When you get an input of -2, you're going to get an output of 2, depending on a different situation. We'll talk about functions later. Now, inverse. What does inverse mean to you guys when you hear that? Reverse, right? That's what I hear, like, reverse. So, if you have a relation is just a specific function, a specific rules where if you plug something in, you get something out. In order to have an inverse relation, it's the reverse of your original relation. So if I tell you to find the inverse relation of the set of ordered pairs, all I'm literally asking you to do is to reverse the inputs and outputs, aka the x's and the y's. Do you see how my input's a -1? My output here is going to be a 2. And then it's going to be a -5. So see how I'm going down, reversing each and every single one of them? That is literally how you find the inverse of ordered pairs. You just switch the x's and y's. That is the very dry, just do it. In the back of your head, I want you guys to be thinking, hey, what I'm really doing is I'm switching the input and output. When I originally have an input, I get the output. But now when I plug in the output, I should work backwards to the input. So it's kind of like working backwards. Reverse. Does that make sense? Now, does everybody know the relationship between a relation and an inverse relation in terms of the graph? Do you guys remember this from geometry? Right? Like it was yesterday, right?
Across, right?
Huh?
Across the y-axis?
Almost. Let's just graph our first relation. Let's graph our inverse relation. Let's see if we can see the pattern. Now I'm going to go ahead and plot these points. This is -5 and 2. So 1, 2, 3, 4, 5. -5 and a +2 is right over here. 2 and 5 is right over here. And -2 and 2. And I'm going to connect these so that way you can see a shape. You see it's a nice triangle there. So ignore this for now. Notice that I graphed the graph of a relation. And if I tell you, hey, I want you to graph the inverse of this relation, of this graph, all you have to do, which I suggest, is to do a couple corner points. A couple corner points are going to help you get the general shape of the graph and just reverse them. Actually switch your x's and y's like we've already done and graph those. It's the easiest way to kind of graph an inverse is just switch the corner points and then you can actually plot them. Because notice what happens. And I'll show you what that means in a second right here after I'm actually done. All right, so what do you guys notice? When we graphed our relation, cool, it's a triangle. Notice that when we graphed its inverse relation, yeah, the shape stayed the same, but how would you describe the movement? Remember those geometry skills? Whoever your geometry teacher, you remember the voice they told you? Do you see it reflect anywhere?
What's the reflection?
There is a reflection, yeah, and that actual reflection is across the y equals x-axis. So if you draw a vertical line going up one over one, up one over one, notice that if you were to fold your paper, and of course it's a little bit easier on your paper than the Promethean board, if you were to flop this perfectly on the side, it will lie right over itself. So, let's keep in mind that whenever you have a relation, you have a relation. It's just a relationship between two numbers. Now, when they tell you to find the inverse, they're telling you to reverse the x's and y's. If you have ordered pairs, it's really nice because you can just take each ordered pair and flip them. Now, graphs, of course, are a little bit more complicated because for me, I'm super visually incapable of flipping things perfectly. My suggestion for you, whenever you're graphing an inverse, choose coordinate points. Find inverse of those coordinate points. And just graph it. Now, I felt like there needed to be some type of list, to-do list here. But the moral of the story here is if you have a relation, especially with the graph, choose a couple coordinate points. That's going to give you the general shape of the graph. Once you focus on the coordinate points, it's super easy just to flip them, and then you can kind of get the shape from there. And that's literally how you could graph them. Of course, you could reflect it over the y equals x axis, but then that becomes a little bit more complicated. I'm really bad at visually seeing those things. I guess my spatial recognition is really horrible. Okay? All right, so we've done ordered pairs, we've done graphs. Are you guys ready to start equations? Nothing else you'd rather do on a Tuesday, right? All right, so before we find the inverse of an equation, I want you to kind of understand what is an inverse to the full extent. Now, notice how you have a function here. Let's choose a random input here. And no, I'm choosing any number that my heart desires. I'm going to choose a number that's quite easy to deal with. I'm going to choose a 0. I'm going to input a 0 into my function to see what the output is. Now, let's go ahead and do that. F of 0 is going to be equal to 0 plus 6 divided by 2. Doing the math, 0 plus 6 is 6. Divided by 2 is going to equal 3. So, what is my input? 0. What is your output? 3. Now, if I told you, hey, this is a relation, this is a function, and I told you to find the inverse function, what equation would you expect, or what would you expect that equation to do? Let me change colors to make sure that you even see it. So, notice that this is the relation. When you input a 0, you get an output of 3. If you're finding the inverse relationship, I want you to come up with a relation that when I plug in a 3, it gives me a 0. Because all it's literally doing is reversing. It's kind of like working backwards. Now, I know that seems super hard. How in the world are you going to find this random equation that switches the x's and y's and makes you work backwards? It's quite easy. And let me show you how. Notice that you have an f of x. When finding inverses, f of x is horrible to work with. Let's just change it back to what we know it's equal to. It's equal to a y. So your first step, I would say, is to change f of x to y, just so that way you can see your x's and your y. Now remember, what's an inverse again? Literally just reverses the x and the y. So if this is a y, I'm going to reverse it to an x. If this is an x, I'm going to reverse it to a y. Everything gets remained the same. Now, of course, who in their right mind likes an equation where y is not by itself? No one. So after you switch your x and y, in order to find the inverse, because technically this is the inverse, I want you to actually solve for y. So solving for y, notice you have plus 6 divided by 2. What's the first thing you get rid of? The 6 or the 2? The 2, absolutely right, because it's all getting divided by So let's do the opposite. When you divide by 2, the opposite is to multiply by 2. 2 times x is just 2x. Again, these are opposite operations, so notice that those divide out and you're left with y plus 6. Now your y is almost by itself. All you have to do is minus 6 on both sides. You end up with 2x minus 6 is equal to y. So just to be a little more comfortable, I like my y on the left side. So that means that y is equal to 2x minus 6. All right, you guys ready for the cool step? Huh? Right? So remember, this was our original function. When we inputted a 0, we got an output of a 3. Now, this is what the inverse does. I like to think of it as reversing. It's kind of like if you have a roadmap, it's the way to get backwards. So you ended up on the output. If I input what used to be my output, so 3 times 2 is 6. 6 minus 6 is 0. So that's literally what the inverse is. It's really just a function to help you get from output to input back. But if you were to do coordinate points for that specific function, you'd end up with just the reverse of your ordered pairs. Okay. Now keep in mind that we wrote this in function notation, so you do have to change your y back to function notation. But we need a way to notate that this is a inverse. It's not just a random relation. And it's actually quite easy. All you have to do is put a little -1. It has nothing to do with something raised to the -1. It's just literally just say, hey, this is the inverse function of whatever function we started off with first. Kind of cool, right? I think it's kind of cool. You're coming up with an equation and kind of work backwards. When you input something, you get an output, and then now every time you plug in your output, you're going to get back your input. So it's pretty cool. Future math, you'll see. I'm not sure if we'll have enough time. I hope we do. You start getting into like logarithms. Have you ever heard of logarithms before? Really fancy term. They're just the inverse operations of exponentials, and you do a lot of math stuff with that. So go ahead and find the inverse of this function here, and I'll go around seeing if I can clarify anything. And this will be our last one. So sorry to rush you guys, but I want to give you guys more time to do your guys' homework and actually get some individual practice. So this is my attempt to kind of rushing things up. So I'm trying to find the inverse of this equation. The first thing I need to think about is, hey, inverse is just switching my inputs and my outputs, aka my x's and my y's. So in order to start working with my y's, I'm going to change my f of x back to y. So y is going to be equal to x minus 3 minus 5. And now I'm actually going to do the inverse part. I'm going to switch my x's to y's and my y's to x's. So that's what I'm going to do over here. It's going to be x is equal to y minus 3 all divided by 5. Now, remember that no one ever wants an equation that's not y by itself or y equals. So let's go ahead and get that y isolated. Do we get rid of the 3 or the 5 first? The 5, let's multiply by 5 on both sides. They cancel out to the right. 5 times x is 5x. Don't forget your y and your 3. Now, solving for that y, all you have to do is add 3 to both sides. You end up with 5x plus 3 is equal to a positive y. Now, I don't care if your y is to the left or the right, but you do have to change it back to function notation. So remember, unfortunately, you just can't change it to f of x. You have to let the reader know that it's the inverse function. But it's really straightforward because all you have to do is add that little -1 on the top right, and you're letting the reader know, hey, this is the inverse function. This is your original relation, your function. This is its inverse function. So 1 is the roadmap to get there, 1 is the roadmap to get back. If you have an input here, plug in the output there, and you'll work backwards to that input. Make sense? Okay.